So now we'll see the last and the most important property of systems, which is the linearity of the systems. So we say a system is linear when it satisfies the superposition property. So what we mean by the superposition property is that, let's say there is a system which produces an output of y1 of t for an input which is x1, and the same system produces, let's say, y2 of t for an different input of x2. Now if I want to find out what is the output of this same system when I combine these two, that is x1 of t plus x2 of t, then if the output turns out to be the sum of the individual outputs, then we say that this system satisfies additivity. In other words, instead of having two different blocks like this, I can just have one block and just sum the signals, okay, and I'll get the output also to be summed. In other words, if I have a system like this, let us say this is x1 of t, this is x2 of t, and these two blocks are exactly identical, then we can replace this entire system with a very simpler block which is of this form. So instead of adding the outputs, we can just add the input and feed to the system. The system will process the inputs as if they were given separately and then added. So the superposition property tells us that a linear combination of certain signals will produce the same linear combination of the output of the corresponding individual signals. So a system that satisfies the superposition property is called as a linear system. So what we mean by linear combination? When we say linear combination, we mean that take the set of input signals, multiply with some constants and add them together. That is what we refer to as linear combinations, basically summing the scaled inputs. So this is called as linear combination. Okay, so linear combination of inputs produce linear combination of the corresponding outputs. Okay. If this is the case at the output of a system, such a system is called as a linear system, and this property is called superposition. So you can define superposition as the scenario or the property under which the sum of scaled inputs produce the sum of scaled corresponding outputs. And how do you check it? You take two inputs x1 and x2 which are not equal. So in this case x1 is not equal to x2. Take a linear combination of them, feed them as the input to the system, observe the output, and if that output is equal to the linear combination of the individual outputs, then you say that the system is satisfying superposition property. And because the superposition property is satisfied, we say that the system is a linear system. Okay, so this is like saying, you take a graph, let us say this is x and this is some y which is equal to some a times x. So this is a line, right? So in one dimension, this is basically nothing at a linear relationship. So you can draw a line and the orientation of the line depends upon this constant a or m, which is the slope. So if I take a particular point here, x naught, and take another point here, which is, let's say, x1. Now let us say this is the corresponding y value. Let's say this is y naught, this is y1. Now let's extend this line, and I want to, let's say, find out the value at some x2, which is equal to x0 plus x1. Then how do we compute the corresponding output? In fact, we can use these values here. How? Because y is equal to m times x, and you know that y0 is equal to m times x0, y1 is equal to m times x1. Y of x0 plus x1 is equal to simply nothing but y0 plus y1. Okay, and this point is y0 plus y1. So the extension of this one-dimensional view is what we get under the superposition. So this one-dimensional representation is for very simple scalars. So if you have x0, x1, x, these are scalars. These are simple numbers, and we have a function of this form, right? Now what if this was a signal? What if this becomes a signal? Right? Then you cannot draw it like a simple graph, but then you'll have a much complicated graph. But the relationship still holds true, and that relationship is what we call it as superposition, right? And the linear combination essentially is very similar to adding these points here. So a generalization or an extension of this simple line concept is what we refer to as the linearity of systems. Okay, you take 2 points, you know what are the output at those 2 points. When you add those 2 points, you still know what is the output at the other point. So this gives a very nice, interesting consequence. It tells us that if I know the output of x1 of t, then I also know the output of a times x1 of t. Now I can plug in any value for a. I can plug in a is equal to 1, 2, 3, 4, 1.5, a is equal to 3 pi, 2 pi, whatever. And the scaled version, all kinds of scaled versions of the signal x1 of t, I will know what is the corresponding output because of this nice property of linearity. So if I know the output of a rectangular function, then I know the output of all the scaled rectangular functions. And if I know, let's say, the output of a rectangular function and a triangular function, then I know what will be the output of all possible combination of these two functions. So this is a very nice way of characterizing a system. Just by knowing what is the output of one signal, I know what is the output of all possible scaled version and combination of these two signals. So this property comes in really handy, and we'll see this later how this can be exploited even further. Now we'll see some examples. Okay. Now let's check if the system here is linear or not. So how do you check? So the output of the system for x1 of t is x1 of t times u of t, and the output for the system for x2 of t is x2 of t times u of t. Now what will be the output of this system when you have a times x1 of t plus b times x2 of t? The output is going to be ax1 of t plus the entire thing multiplied with u of t, which is exactly the same as the individual outputs scaled and added together. So this is a linear system. Great. Now what about this system? So once again, let us see y of t is a times x1 of at plus b, and y of 2t is a times x2 of at plus b. Now what if you feed in x1 of t plus x2 of t, then you get a times, okay, let's make this a naught b naught, a times x1 of a naught t plus b naught plus b times x2 of a naught t plus b naught, which is exactly the same as a times y1 of t plus b times y2 of t. Here we are saying that x1 produces y1 and x2 produces y2, and ax1 of t plus bx2 of t produces y of t. So clearly this system is also linear. That's nice. So which means that time scaling and time shifting operations, they're all resulting in a linear operation, which is quite good to know. Right, now let's see this final setup. So y1 of t is just dx1 by dt. So we already saw that differentiator is a very practical setup, and then we know this property very well already from our earlier high school math, but then anyway we'll just check it out. So this is simply d of ax1 of t plus bx2 of t by dt. This is necessarily a1 now. So which means this also satisfies the linearity property. So the linear combination of the input, you just take them and take the derivative, it produces exactly same as the linear combination of the output. So this is nice. So we have a set of linear systems here. Now let's see some more examples. Now let's take this case. What is y1? y1 is t squared x of t plus c. y2 is t squared x2 of t plus c, and y of t is t squared ax1 of t plus bx2 of t plus c, which is not equal to ay1 of t plus by1 of t. Why is that? Because there is only 1 plus c here, but when you add them together, you get ac plus bc. When you add these two things together, an extra term which is not the same as this. So it is interesting to note that this t square term is not what is resulting in the nonlinearity, but the plus c term is what that is leading to nonlinearity. In other words, even if we had removed this will still be nonlinear. Okay, so just by adding a constant plus c, we are making this setup completely nonlinear. Okay, so this is nonlinear. All right, now let's see the next example. So y1 of t is tan of x of t plus c, and y2 of t is tan of xt of x2 plus c. Now y of t is tan of a x1 of t plus b x2 of t plus c. Once again, this is clearly not the individual terms added together, right? Because tan of theta plus some phi is not equal to tan theta plus tan phi. So once again, this is also a non-linear system. Now what about this scenario? So y1 of t is equal to x1 of t times x2 of t plus so this is the procedure with which we check a particular system is linear or non-linear. Basically what we are trying here out is we are trying and checking its superposition property, right? So now this is once again, this is definitely not equal to y1 of t plus by2 of t. Why is this? Because when you multiply, you get a square x1 plus b square x1 x2, and then you get the cross terms, right? You get terms like x1 of t with x2 of t plus t, which is never there in these terms. So clearly they are not equal, and hence this is also a non-linear system. What about the final setup? So this is a tricky question. When you look at it, it appears as if it is a linear system, but actually it is not. So let us see what happens. So y1 of t is equal to real part of x1 of t, y2 of t is equal to the real part of x2 of t. So because you are taking on the real part, necessarily this is a complex signal, right? Because this is complex, the scalars with which you are going to multiply them, this a and b, can be complex. Okay. So these two can be complex. This is not equal to a times y1 of b plus b times y2 of b, because these can be complex numbers. So what we have here is the output is always a real number, right? But this combination, linear combination, can be a complex number. This a and b can be complex numbers. Because we are working out with complex numbers here, the signal is complex. These coefficients a and b, the scalars that with which we are multiplying, can also be complex numbers. So when we take linear combination like this can be a complex number, but the output says it's always a real number. Clearly they are not matching, and hence this is non-linear. So we saw different properties of systems, namely causality, memory, invertibility, time invariance, and linearity. Now the three important components in electric circuits are the resistors, inductors, and capacitors. Now let us see what are the properties satisfied by these systems. So when we consider them as systems, what do we mean? So we say that we'll connect these components in a circuit like this, and we apply a source and observe the output across these properties. Now when we observe the output across these components, do they satisfy causality as a system? Yes. Resistor, capacitor, and inductor, they satisfy causality. And what about memory? Clearly resistor does not have any memory, but of course inductor and capacitor, we saw that they could be modeled with a differentiator and integrator, and hence they do have memory. Are they invertible? Clearly, once again, because the capacitor and inductors are modeled through the integrators and differentiators. They do not possess the property of invertibility. They are not invertible. But the resistor is a very simple component, it is invertible. And following the same notion, because the capacitor and inductor are modeled using the derivative and the integrative operations, they are time invariant and they are linear. So as you can see, all these components satisfy these three properties simultaneously, and hence we'll focus in the future on systems which has these three properties together. In fact, we'll focus more on the time invariant and linear properties together, because all practical systems are anyway causal, so we'll take that for granted. So we'll focus on systems that satisfy these two properties and then study more in detail about the systems which together simultaneously satisfy linearity and time invariance, and we'll call such systems as LTA systems.